Okay, before the break, we were looking at uh, the components of a network, the physical components, the machines we connect together, how we connect them together, why we connect them together, all of that good stuff. Um, but then what do we do with them once they're there? There's another big question. So we before the break, we looked at the different ways we can connect them, the most important pieces. And again, this is an introduction class that usually means a lot of vocabulary. And this is the introduction to all of the School of IT. So very quick pass at some of the most important vocabulary. And next thing is the protocol. How do both machines know what that data means? We talked about this in the hardware section. I think I reiterated it in the binary when we were talking about binary. That is unique for the machine. Machine language is specific to a machine. It's not like we can say, okay, this is an HP laptop, so the machine language running on this is going to be the same as other HP laptops. And it's not. Has anybody ever had to go in their BIOS on their machine? And if you go to look up instructions on how to get to the BIOS, you don't get instructions that say, okay, press a certain key. Like I'll look it up for this machine. If you haven't seen it. How to get to BIOS. That's basic in-out system. So that's the pure hardware level for HP laptop. So there's sort of a list there. Our computer startup. Oh, here's a good one. F2 or delete. F2, maybe delete, could be F4. But you'll notice it returns a list of things that might get you there. And that's because the basic in-out system, BIOS, that is unique to the motherboard. And not just the motherboard, it is unique to the particular manufacturer of motherboard that you have. So I have this HP.
They can differ between boards in the same manufacturer.
Yes. So wherever they ordered it from, right? This one doesn't have a name on it. This was cheapest one at Walmart. So I'm just going to call it basic. I'm just going to use the phrase laptop. There's probably a name. I don't know what it is, but basic HP. They made millions of them, right? So they called up factories in China and said, okay, we need 20 million of this board. And the first factory said, okay, we can do about 5 million of them. Like, okay, well, we'll take all of those. And they called up another factory, like, yeah, we need 15 million of these motherboards. Next factory, maybe they don't have as many other orders, so they were able to handle 10 million of them. They go from different factories. And those determine which key press it is. So it's probably something on the top row. And if you're on a laptop, you don't need the function key to get to the F ones. It is actually that key connects directly to the circuit board inside of there and activates the BIOS. And you have to press it at a certain time or restart it. But it's unique to the machine. So if we take the data from this machine, where everything's unique like that, and try to transmit it across the network, try to transmit it across a network over to Hunter's machine, how do I know it's going to work whenever he gets it? Because remember our definition with networks, we're not sending data, we're sending information. And that's where protocols come in. There's lots of them, lots of different ways to connect. But since for the quick intro to networking like we have this evening, to fit in the next, I'm hoping 30 minutes, might be a little bit longer than 30 minutes. We have TCP IP. So actually 2 different protocols. I'll start with IP, Internet Protocol. So picture this, late 1960s. It was long before any of us were born, but y'all are aware of what the world was like in the late 1960s, right? The Cold War was at its height, and nuclear weapons had been getting bigger and bigger and bigger. And eventually it hit the point of mutually assured destruction, MAD, where the weapons had gotten so big that we knew nobody was going to survive, or neither society would survive once an attack happened. It was going to destroy everything, and there'd just be a few remnants around. Well, naturally, the U.S. government wanted to make sure they could keep fighting the war at that point. They didn't want that to spell the end of the war. They wanted to be able to still fight, but that's a whole different philosophical and ethical issue. But they wanted to continue the war, so they wanted to finance something that would keep that going. Like, we don't want to lose communication when we destroy the world. We might still need those. So they wanted a communication protocol that could withstand a MAD situation, that mutually assured destruction. And what was eventually proposed was known as ARPANET. Advanced Research Projects Network is basically what it stands for, but it's very pronounceable. So, and what it stands for isn't as important anymore, right? It stood for something 50. It was this was an acronym 50 years ago. I mean, oh, it wasn't 50 years ago. 1960s. This was a meaningful acronym 60 years ago. Those words don't necessarily apply anymore. So we just say ARPANET, and well, our communication channels are based on, there's multiple sites, right? So I'll just label them like A and B. I'll go in alphabetical order: A, B, C, D, maybe a couple more down here, E and F. So we have these 6 sites that we need to communicate. We want communication to last between. And in an ideal situation, like before the Cold War erupts to complete destruction, we likely have a fully connected network here, right? There's wires and some sort of communication channel running from each one of these sites to every other site. So we have this fully connected network, but how do we continue communicating across that if it's not so fully connected, like after the Cold War fully erupts? So let's say we want to send a message from site A to site B. Well, as a human, we're going to look at this and see there's a straight line channel across there, but the machine's not intelligent. It can't do that. So we need something that's very simplistic and will continue to work reliably. So instead of taking the most direct route, we include in the communication enough to pick the best route. So it will automatically pick the best route. Has everybody heard ping before? I know every single one of y'all has mentioned being a gamer, so you know what pings are. That's just, we send one bit to another machine, and then it responds it gives us a 1-bit response, or it doesn't give a response. And we can measure how long that response took to get back and stuff, but a very simple response. So what we do, if we want to go from site A to site B, we start by pinging every machine on the network. And the first one to get back, we assume that is the best route. So we're site A, we want to communicate to site B, we ping every machine on the network, and maybe C is the first one to respond. So we take that channel. And then it repeats. It adds a little bit of information. Said, okay, this message is coming from site A, needing to go to site B, and it has passed through site C. And it just pings the network. Who's listening? Maybe E is listening. That's the first response, so it sends it there. And then that fits that protocol the government wanted, because it automatically finds open routes. It doesn't just have a list of the best routes at every step along the way. Then maybe site E hears back from site B first. So then it arrives at its destination. And every step along the way, it is picking the route the whole way. So it fit that need the government was looking for. Maybe the next one, it sends it out, site F responds first. And then that hears from site E, site C, site D, and then that hears from site B. So it might bounce around the network for a while, might be quick. One of the things on your lab this week is to do the same thing twice and compare the route it takes. See if it goes through the same route both times. Sometimes it will. More often than not, it will not, because there's lots and lots and lots of things connecting our network. But it fit that need the government was looking for, and it's very easy to implement. Just a little bit of information about where it's coming from, where it's going, and all the machines it's been to along the way. So maybe a third time in that disastrous situation, we're going from site A to site B. So maybe site E, A hears from site E first, so it sends it to site E. And then E hears from site D first, so it sends it to D. And then D pings everything, and it hears back from site A. And it's like, oh, well, it's coming from site A, so don't need to send it there. And here's back from site E. It's like, well, it already passed through site E, so don't need to go there. So then it'll try again, ping every site on the network. It only hears from site A and site E, and that's a confirmation that there is no open communication channel lines left to get from A to B. So then it can very easily return back the route it took, go all the way back the route and tell site E there's no way to get to site B anymore, and go back to the sender and notify it there's no way to get to site B. So it covered that original need they were looking for. And it's very, very easy to write the code. You could read there are pages, books written on it over 1,000 pages long. It's 19 lines of code. Anybody heading into a 4-year degree, if you go to IUS or U of L or Campbellsville or Bellarmine, I don't know if Sullivan does, but I highly suspect they do. So Purdue definitely does. You will have to rewrite IP protocol. Like at IUS, they give it to you in C++ code, and they tell you to rewrite it in Java. It's 19 lines of code. When you write that 19 lines of code, you will understand it way better than reading a 1,000-page book on it, because that's just the instructions it's carrying out. It's not complicated, so it's very simple, and put it in English takes a little bit longer. So that was a great way to communicate. And we can even include checksums in it. A checksum is just an extra bit where we confirm the parity of it. Right? We choose one, say even, and then we're sending a bunch of ones and zeros. If we add all those ones up, it should either be an odd number, or it could only be an odd number or an even number. And then we have one extra bit just in case we need it. So we just set in our protocol, okay, everything's going to be an even number. So if we have an odd number of bits, we turn that extra bit to a 1, gets over to the other machine, and the other machine can just add the bits together and see if it's an even or odd number. And if it gets an odd number, it knows something went wrong in transmission. Have y'all ever sat and waited on a website to load up? Seemed like it take longer than it. What's going on there is the computer is going, something went wrong, send it again. Something went wrong, send it again. Something went wrong, send it again. So that's built in here. We can do little checks and confirm that, okay, just that parity check. It's like, oh, that was supposed to be an even number of bits, and I just received an odd number of bits. And send that data again. It's no problem for around Earth, right? We can get a signal all the way across Earth. We can have a signal loop around Earth several times, way before a human would notice, and way too small a timescales for us. But for other situations, like that camera we sent to Pluto, right, it's past it now. It 8 years past it now, and it's still transmitting data. A good testament to how empty space is. It's the fastest any man-made thing has ever traveled. A speck of dust would utterly destroy that thing. It's gone 8 years past target and still hasn't hit a speck of dust. but it's a camera, right? We were going for Pluto, and on the day it passed Pluto, it was 4.5 hours for the communication to go each way. Something went wrong. Send that high resolution picture again is not feasible if we're talking 9 hour round trip communication. So that has error correcting codes built in. That's one of the things I would have talked about Thursday if I didn't have the meetings. We wouldn't have actually done much on them, just looked at some concepts on a simple one, but in the math class where I had to learn them, on test day, when there was a bunch of other things, it was a combinatorics question, like combinatorics class. So on test day, when there was a bunch of other stuff, we had to create an error correcting code that would correct 3 bits. So they're not complicated to write them. It can fit as one test question on very, very quickly. But it is a bit more advanced math than you're required to know here. So we won't actually dive into doing that. But at the same time, it shows up in a combinatorics class. And combinatorics is a fancy word for counting. Basically, the different ways we can count things, and that applies to probabilities and all that. But we'll sidestep. So that's Internet Protocol, or IP. How the machines kind of connect to each other. We also have this TCP part. This one has gone through a lot of other things. Pretty much everything since this was developed in the late 1960s has used the IP. Transmission control protocol, on the other hand, is not so simple. It's not just a super simple thing that can be developed in 19 lines of code. It's a little more complicated. It comes with tons and tons and tons of overhead. So when it was developed in the early 1970s, I think, I'd have to go look up the date again. It could have been developed in the 60s. But when it was developed, it came with a lot of overhead. So it was like object-oriented programming. It was developed in 1962, but the typical computer couldn't handle all the extra work that came with it until 1985. Same thing with TCP. Around the same years too. It was developed a couple years after object-oriented programming, at least theoretically, and it worked great on the supercomputers, the late 1960s, early 1970s supercomputers they tested it on. But the typical average computer could not handle it up until the late 80s. By the time the late 80s, the average computer could handle it, it's pretty much been the standard, and we haven't looked back because it works great. But it's not a small, lightweight thing like IP. So IP has worked with a lot of other protocols along the way. And what this is a way of breaking down data into packets to transfer and be reassembled on the other side. So I'll do that with a picture. So we have this big file that we want to transmit across the network. Instead of transmitting that whole thing and hoping it makes it across the network successfully, we can break it up into little pieces. Let's do something like this. And these are not logical pieces. It's not like this is one function that the software does, and this is another one. It's like maybe this is the first 198 bits, and this is the next 1024 bits, and then this one's the next 200 bits after that. It's not logical for the software. It just breaks it up into little pieces and sends each piece independently. So this piece will come across the network. And on the other side, it gets rebuilt as best as it could. And grab enough colors, maybe. Then this piece, using IP protocol, takes a different route across the network. I like to exaggerate it in this picture. Maybe a blue piece here. Comes around, takes a different route through the network and ends up over here somewhere. Got a black piece coming through our network and fills in this little gap here. What's that? Oh, here, like this. Don't quite have enough colors. Then our last piece takes its own, and it passes through the network as an independent thing, and then they can be reassembled on the other side. Perhaps not perfectly. Images are a good example of that. A lot of times, depending on our service, we might go ahead and pre-configure it. We have highly detailed images. And it's like, try to send the super high definition image. But if anything fails, then compress it and lower the quality a little and send the smaller version. And keep doing that. So it might not be a perfect replica on the other side, but in general, everything should make it back across the network. That's the core idea of each OSI model. We break it down into these packets, and each packet then uses the IP protocol to find its own way across the network. So the data is not taking the same route itself either. Every one of those packets finds its own route across the network and then gets reassembled on the other side. So we need a few things in order to do that. And turn from here, yeah. So in order to do the reassemble part, is breaking it down is easy. We just grab a different number of bits. It's not a logical breakdown. We don't have to worry about what the data is for or what software uses it or anything. We just grab a bunch of bits and that's our chunk. Then the IP protocol is very, very easy. There's several versions of come and gone. Version 4 is the one that really took off. The reason version 4 took off is because they used a selection structure to determine whether it was on the sender or receiver. Versions 1, 2, 3, and 5 use different code. There's sender code and receiver code. So both machines have to have both of those. And they send and receive them differently. But with version 4 and then version 6 followed suit from that. They just put a selection structure in. We saw that last week, right? The binary choices. And it automatically determines whether it's on the sender machine or the receiver machine. So the same code runs on both machines. That's why version 4 and 6 really took off. Those are the ones that are 19 lines of code. When we break it down, and so one was kind of the prototype original designs. 2, 3, and 5, those aren't 19 lines of code. Those are probably more like 35 lines of code spread amongst 2 files. Because most of it applies to both sides, and we have to duplicate it for software for both machines. So that part's easy, but the reassembling it is a little bit harder. So to reassemble it, that's where all the extra stuff comes in, and there was a 20-year delay in implementing that after it was invented because machines couldn't handle it. So each packet is padded with what's known as the OSI model. I can't remember what OSI stands for. What does OSI stand for? Open Systems Interconnection. So it doesn't explain what it does. That sounds like that was named after the company that invented it. That's probably why I didn't add it into my notes. So it's just the name of the people that invented it is what OSI is. And what this has is 7 different layers. I'm going to start at the bottom. At the bottom, we have the physical layer. And the physical layer is the bits making up the data. So that's our pure data itself. So that's all of our little chunks. I'm gonna call them chunks at this point. And then packets are what we have in the OSI model when we pad them out. So our chunks of bits, probably 1024 bits in each chunk. It starts at the beginning of our file, since the first 1024, and goes, then grabs the next 1024 bits. Each one of them is starting to form a packet. So the physical one, what actually goes on the machine. But back to the beginning of the night, we don't transfer data across the network. Networks are for information. We need useful data. So right above that, we have the data link layer. And data link is the format in transit. So we have our bits and we break them up, and how do we format them across the network? We didn't do anything with HTML. At some point, software developers will definitely see this. So that's your get and your post and your put and request and file, and the method by which you're sending your data across the network. After that's the network layer, which is the physical path taken. So it is actually a step up from what's built into the IP protocol. It's an improved version of that simplified one I talked about earlier. But unless you're going really far in networking, you can just think about that's that IP protocol. The from site A to site B have already visited site E and D. The actual path that's taken, but as you progress that further, there's improvements from the original IP protocol in the OSI layer. Transport layer is right above that. And the transport layer is protocol data. So if you see it on a multiple choice quiz, the answer is going to say protocol data. But for a classroom, it's like, what does that mean? That is packet size and number. So not the number of packets in our overall data. So that's like, okay, this packet is 1024 bits. It has even parity, and it's number 6 when we go to reassemble it. It's the 6th one in order. So the size of it and then the number of bits it would have, and the parity. So there's 1 extra bit, so that if we're supposed to have an even number of bits, we can put a 1, and we have an odd number, we can put a 1 there when we send it, and then count them all up on the other side to confirm that it came through okay. Session is the 2 machines connected. Which one of the machines is the start and which one's the end? And it's not like just the from A to B, it's at every step along the way. So on the IP protocol, if it goes to E first, we have a session going from A to E. And then if B's the final destinations afterwards, then we'll have another session happen. So which 2 machines? Where's it coming from? Where's it going? Not all the way across the network, just the current step. Right. Packet number 5 has 1024 bits, even parity, and it started here and is going here. And does that at every step along the way. Presentation. So this is the rest of that parity thing. The sequence, the checksum, so we actually added up here. I should write this off. It's spread out amongst those two. We actually do the confirmation here, but there's going to be an extra bit here. So it's 1,024 bits plus 1 for the parity. And then information about whether that parity is at the front or the end, different things like that. Encryption goes here, encrypt, encryption, decryption, take care of that there. The actual format of it. What does this data look like when we put it back together? And not the final result of it, it's instruction, because this is the instructions on how to put it back together. So sort of hints at what it should look like. The packets are numbered 1 through 12, but they're not sequential. We're going to do all the odd ones first, then the even ones to confuse anybody that might be trying to receive them. They have even parity, and they're encrypted with a Vigenère cipher, a simple Vigenère cipher or something. We have that information here, and it is spread out amongst all our packets, so you can't receive just one packet and figure out what all that stuff is. And then at the top, we have the application layer, and that's the software we use. What software does this open with? Right, if we're sending a PDF, the file extension, we're sending a PDF, it opens with whatever the default PDF viewer is. If it's a document file, it's going to say which form of document file it is. They're generally compatible, but it's going to say maybe it's coming in ODT. So it's coming in the form LibreOffice saves it in, and Microsoft Word and Pages and Google Docs all know what to do with that form when they get it. So we have all the information we need to put it back together. So that's the OSI model. And your network, the one networking class everybody has to take, you will talk about that at length. And then in the future networking classes, you'll get into super fine details of it. But we pretty much use those. It's easy to implement. There's a little overhead, but not much by today's standards. In the late 1960s, early 1970s, whenever that was created, it was way too much overhead for our machines. Right, we were talking a megabit of RAM was probably the most powerful computer on earth. So a little bit of overhead went a long ways back then. But by today's standard, it's not much overhead. Still quite a bit, but once machines could handle it about 1985, it pretty much became the standard. We use TCP to break down the data into packets, and then we send the packets with IP protocol, with IP. So each packet finds its own way through the network. And there's one more piece of information we need to connect. It's okay if I erase this first slide over here? Hopefully. Then the last thing is, how do these machines actually connect to each other? That's where ports come in. So ports are how we connect for different purposes. Purpose we're connecting for. Sounds like a good sentence for the notes. It's a software-based 16-digit number. Sorry, 16-bit number. Both machines agree on. So I mentioned that those who continue under a 4-year school, you will definitely have to write IP protocol. And they'll give it to you in C++. And one of the conditions is you can't use the existing ports for IP protocol. So port number 80 is HTTP traffic. or 443 is HTTPS. They have different meanings. There's some important ones. Generally, we make it up. Port 3306 is a MySQL database. 2480 or 2408. Can't remember which one right now. 2480, I think, is Orient DB. It's a powerful non-relational database. Port 22 is SSH. That's a very important one. Secure shell. That's how we connect to another machine and use the terminal on our machine to run that other machine. I did it very quickly the other day when we were looking at PowerShell. One of the things I pulled up was on PowerShell to show there's a Boolean in there called virtual host enabled. As long as virtual host enabled is set to true, then that means you can connect to another machine through port 22 and control that machine from your terminal is going to transfer over and control that machine instead of the local one. 53 is DNS, domain name service. That's computers know about each other because of long strings of numbers that humans would never possibly keep track of. So we put human readable names on there, and then they're just if machines connect on port 53, that means we're looking for the human readable names so that people can interact with them. It's to the point that if you tried to type in the numerical address for a machine that has a known name, it'll trigger security protocols because computers know that, or somebody hard coded in the computer that humans don't type physical IP addresses if there's a word to access that machine. We use the human readable ones. 80 is HTTP. 443 is the secure hypertext transfer, HTTPS. 3306 is MySQL. That's what I got on the list here. And we can just make up whatever number it is. So those heading on to a 4-year school, when you have to write AP protocol, the condition is that you can't connect IP across port 80, 443, 53, or 22. That's probably explicitly what it's going to say in the instructions because that's the standard ones to do it. So most people do something simple to do it on like port 5555 and just make up something because the 16-bit number is pretty large. 2 to the 16th is a fairly large number. So we have lots of numbers we can just make up. And as long as both machines know it, that's the agreement, right? That's saying which door to use. It's not different wires, right? It's not the 80th wire plugged into the machine. It's a label we put in the software side that both machines agree on. Important thing, you want to remember a few of them. I think I could put some more in here. 21 is important. 21 is FTP. Though FTP will also transfer across SSH fine, so a lot of people just open up SSH and they don't have 2 ports. They only have 1 port open instead of 2. Or some people will do the opposite and put SSH on the FTP port. That way people don't already know what port number to use to connect it by SSH. As long as both machines know about it, that's the agreement. I guess it's the meeting place, right? The 2 machines, both sides of the network. If we're going to connect terminals and control the machine on the terminal, they agree to meet on port 22. If we're doing stuff with a MySQL database, both machines agree to meet at port 3306. That might be one way to think about it. That's a quick pass. Some of the most important things, the terminology you will see over and over and over again in quizzes, explanation on what those are. Everybody has to take a networking class, so sort of preview mode here. You will have more networking. Hearing it repeatedly is where we learn it, right? I certainly don't expect you to hear it one time and remember it forever. Repetition is an important part of the learning process. But does anybody have any questions about those things we looked at tonight? questions or comments, anything like that? Okay, I assume 5 seconds of silence means no questions. If you have any, let me know. For the rest of the week, I'll be in Indianapolis. I won't be as quick as normal to answer my emails, but I will still be checking them every chance I get. I just don't know how often that's going to be. And otherwise, then I'll see you all next Tuesday. What are we doing next Tuesday? Let me pull that up and do a quick preview of what's next. Oh, in the lab this week, you're going to do some networking things in the terminal. I wrote up the instructions for different machines. We looked at PowerShell last week, so that works on every machine, so you can just use that one for consistency, or whatever terminal you have on your machine. Open it up, type some command prompt instructions, and send me screenshots of those. Some basic networking instructions. Those are straightforward. Software, networking, and next up is cybersecurity. Yeah, so next week we'll get into cybersecurity, and for this class, that means lots and lots of definitions, lots and lots of important terms. I tried to make the lab interesting. I found a couple of interesting things to do with the lab, but when we're talking about it, it is very much a definition lecture. It's not even pictures to draw. Maybe some pictures, but it's gotta cover it somewhere. So that'll be next week. A lot of people are excited about that one. There's a lab step-by-step thing like normal. If you have any questions, let me know. Oh, I'm not sharing my screen, am I? Sorry, let me share my screen. Here's what I was looking at. So this week's networking, got a step-by-step lab, discussion board, talking about how important are graphics, right? Nobody wants to read tables of data like we looked at in the database lab. We want to see nice pictures on the graph. What can we do with that? I'll have some comments about that afterwards. Yeah, there are ways we can use. Color theory has a lot of effect on people. So I will talk about that some afterwards. Post on the discussion board. Please post on the discussion board sooner rather than later. Once again, this week, there wasn't really much that could be replied to. And I thought it was a really interesting discussion board this week. This week was the ChatGPT one. But please post on those near the beginning of the week. It's not going to be points if you waited until the very end of the week to post anything there. And next week we'll be in cybersecurity. A lot of people are excited about that section. It's a definition lecture, but it's words, the definitions of things that a lot of people care about these days. So I assume there's no further questions or anything. Y'all have a great rest of the week. I will see you next Tuesday.